Yeah, you can. Thank you, Jagdish, and thanks very much to. I think it's on, right? Is it on? Yeah. So, and thanks very much to Aries and all the people in Aries for having me here. And I've been here 5 years back. It was a very short visit. I do remember a few things from that also. And many things have changed. So, I got a position in IIT Bhilai and then started opening up other areas there. So, it's a pleasure to be back and it's a pleasure to share my research with the community here. So, the topic of today's talk is reionization, which is a fairly, I would say 25, 30 years old problem. And but as you all know that JWST is now in operation. So it was launched finally, and in 2022 and 23, it started generating a lot of data on the very high redshift sources, both the AGNs as well as the galaxies. Okay, and what information it is providing and how it connects with the theoretical research that have been existing and that we are currently also doing. So that is the topic of today's talk. Okay, so actually the work that mostly I will be presenting today has been done with Nachiket. I think he was here in Aries at some point of time. I do remember doing some project with some of the Aries faculty, and so he is working with me right now on this particular problem that I offer to him. And most of the simulations and calculations are actually done by him, and I was also supervising him through the problem. So let's get started. Right. So this is a picture that you would have seen in multiple talks, which is the history of our universe. So basically, the universe starts in the Big Bang, and then it has the initial very hot phase, and then at some point it expands rather exponentially. It is called the inflationary period, which is shown by this from the point you expand all the way to that much, and then it is gradually cooling down also, and then there are inhomogeneities in density that are present in the dark matter that is the main component of the universe. They are also developing as the universe is evolving from these very high redshifts to low redshifts. Then at some point of time, which you see as this the surface, which is like kind of a green surface, and it's purely a surface, roughly at redshift of 1100 or so. When the which is called the last scattering surface, when the neutral atoms, basically electrons and protons recombined, and then the neutral atom formed. So then photons can no more scatter of the charged centers, and all the photons were liberated. Previously, before that, they were all locked up in scattering process in the plasma of the universe that existed. But once the electrons and protons they combined, then after that the universe became neutral and photons were liberated. All of a sudden, this is very, very sharp at redshift 1100 or so, which we know as the cosmic microwave background radiation that was emitted or that was liberated. Not emitted, I would say liberated. It was always there in equilibrium with the matter, and then it became free. So also you see that particular surface could have been just a single color monotone, but it is not. There are, you see this yellow patches and then some blue patches and some dots are there in this particular surface. That basically tells you about the density inhomogeneities I was telling. So the last scattering surface has the imprint of all those small inhomogeneities. That is the main, bread and butter of the CMB research, to figure out the characteristic of those inhomogeneities, which are the basis point for all the structure that exists today in the universe, like the galaxy. So then the universe entered in this neutral dark phase. We couldn't see anything. And then all the inhomogeneities that were seen at that CMB, they kept on growing. And at some point of time, the inhomogeneities or these density perturbations in the dark matter, they became nonlinear. And then they started collapsing onto their own. Basically, they separated from the Hubble flow or the expansion, and then they started forming these density potentials and structures, which we call as dark matter halos. Now, the baryons, they followed in to these potential wells, And then some way, initially it was all hydrogen and maybe helium. And then somehow still the baryons managed to cool and start forming stars. And we think that the first stars were very metal poor, probably population 3, probably population 2, but some very metal poor stars. They formed in the first galaxy. Okay, so the universe was dark, and then this happened. This happened roughly at a redshift of, I would say, the galaxy started forming about, it's 20, let's say. Okay, but the JWST is pushing this boundary. So you never know, within 2-3 years or so, you push that to 25 or something. Okay, but nonetheless, it's about 20. Okay, so CMB at 1100, and this is at 20. So the whole epoch of reionization is basically this period between 20 and it finishes at 6. Okay, what is reionization? So you form these first stars within the first dark matter halos or first galaxies. The galaxies produce UV photons, and then stars are predominantly massive stars, so they produce a lot of UV photons. Those UV photons, they go out of the galaxy, out of their dark matter halos, into the intergalactic medium, which is all neutral after the CMB. And then these UV photons ionize this intergalactic medium, and the universe transitions fairly rapidly at redshift about 9 to 6 or so into a ionized state, almost ionized state. 99 so 1 minus 10 raised to the power minus 4. So I don't know, 99.999 something, that percent ionized, it becomes almost ionized. So yeah, so this is basically in a very simplistic picture about reionization. So this is the brightness temperature of the gas. So let's not go into that one. This is the rather simple one. So this is the ionized fraction of the gas. This basically ionized. Then at CMB, it decays down to almost 0, becomes neutral. And then at ionization or the reionization, which is the red phase, I have rather drawn it rather elongated, but this is also fairly rapid. Between 20 and 6, it becomes ionized again. Okay. In the brightness temperature, you have to think whether the gas is coupled with CMB or not, or at some point it decouples and then heating begins before the actual reionization begins, and then the heating picks up, and then the reionization begins, and the reionization ends. That's the whole picture that you have. Okay, this is from the Planck satellite. So when ionization finally happens at redshift 10, 9, 8, or 6, the free electrons from there, now they are traveling towards us. Okay, so what basically it measures is the optical depth backward, looking backward in the universe, and then you try to see where the universe was neutral. You calculate the total optical depth. So that comes from the polarization measurement of the Planck satellite, from the space-based Planck satellite, and it can be inverted by using some sort of modeling. The modeling here is this shaded portion, and then there are some observations of the quasar spectra. So that tells you that the reionization must have happened between redshift, would say 9 and 6. Okay, so that's the rough temporal scale where the reionization happened. It converted from the neutral to the ionized state. But that I am not 100% sure right now, but not just polarization. So the first thing you measure is the Thomson scattering optical depth. The polarization aids to it. So that I know. How exactly? So I don't remember top of my head. I have to look at that. So there are two things here. The major constraint comes from the Thomson scattering optical depth of the free electrons. When the second one, it is narrowed down by using the polarization measurement. Okay. So what are the candidates that ionize the universe? Okay, so the galaxies and quasars. So those are the two potential candidates, because you formed probably supermassive black holes at the same time, and they had a lot of radiation coming out from them. And then there were galaxies also. So you ask the questions, what ionized the universe, whether it was the quasars or the galaxies. So the quasars cannot do it, and this is a simple reason for that. So this is the number density of all the objects that exist. The galaxies are shown by the dashed curve, and the quasars are shown by the red curve. So the quasar number density, as you go from low redshift to high redshift, it drops down drastically, and the galaxy number density is sustained. Okay, so that's the picture. There are some challenges to it. There are some higher measurements of quasars that are probably pushing this red line above, but nonetheless, compared to galaxies, the quasar population is pretty low at redshift 6, 7, 8, or 9. So quasars could not have done that. So the galaxies are the leading candidates that actually reionize the universe. Okay, but you ask the question, galaxies are not a single class of objects. They are all variety of galaxies that exist. Starburst galaxies, big galaxies, small galaxies, luminous, faint, this or that, okay? So which galaxies would have done it? So that is the main problem you want to figure out, like how galaxies did it and which galaxies did it. The second thing is how galaxies form. So you have the simulation evolving. You would think it is the luminous matter, but it is not. The blue shows you the dark matter, okay? And how the perturbations are going in the dark matter. So each dot finally from very high redshift to, let's say, redshift 6 or so, the universe is having these nodes or dots, which are dark matter halos. Okay? And then the baryonic matter settles into those halos. You want to figure out how much star formation will be there, and corresponding to that, how much will be the luminosity of the particular galaxy, and what will be the mass of corresponding dark matter halo. Okay? So that's the main thing. It's a big factor. You have a dark matter halo mass, then how much baryons go in, and how much is the star, and what is the corresponding luminosity, corresponding UV photons. You count all those UV photons, and then you try to ionize the universe. Okay? So these are the number counts of the dark matter halos from a leading cosmological simulation. And then there is a side-by-side semi-analytic work using Preshechter approach. So the left top, this plot, which is for the number functions of the dark matter halos, how many dark matter halos of a particular mass. Far too many at the low mass, and a fewer dark matter halos of a higher mass. Now, there is literally no question about that one, okay? If you have faith in the weakly interacting massive particle as the dark matter constituent, and you have significant faith in the cold dark matter lambda CDM universe, then that theory is very well settled. Nobody questions that those many objects, dark matter halos, would be there, and it has been established from multiple simulations and by multiple groups. You can always say, I don't consider cold dark matter to be the leading thing. It is the hot dark matter or warm dark matter. But then eventually there will be changes on that, but lambda CDM is the accepted model. Halo mass. So halo mass, that's a very good question. So this is the theoretical work, okay? This is purely theoretical work, given that the total universe has perturbations, and then how many dark matter halos you will form. You never measure the dark matter halo mass for high redshift halos. You can do it for Milky Way or for nearby galaxies by looking at the rotation curves from the dynamics of the stars. And that is also kind of an indirect measure. But you can never measure the dark matter halo mass anywhere, literally. But the theory is well established. I mean, theoretical point of view is very solid, and that is the result that we get from there. What we see are the stars. There is a big bridging has to be done from that plot to this plot, which is another simulation, very famous one on which I was working. It's the Eagle simulation, which is a cosmological simulation, in which now you have the dark matter, those many numbers sitting somewhere in the universe, and then you start populating them with baryons, and then baryons form stars and visible galaxies. The simulation takes you from redshift 20 to redshift 0 to match all the properties of the galaxy that we see in the universe, like the luminosity functions, the stellar mass functions, and all metallic properties also. It does a very good job. Correct. So I think the way the local group of galaxies like ours, for it has been this job has been done, counting how many satellites. It is, in fact, it's reverse also. It helps also to tell you, are we missing some satellites that should be there, and that also has been verified. So that is well established for the not just our cluster, but other clusters also probably. So yeah. Right. So given the dark matter halo mass, which is the x-axis, the simulations produce the quantity that the observers want, which is the stellar mass, or the intermediate quantity, the star formation rate. And this is the stellar to dark matter halo mass, which is from the simulation. So you get this trend, and it has been compared with the observations also. For the reionization purpose, how is the reionization problem attempted? So what you do now, I'll tell you the the basic idea. So basically, you have to now count how many photons exist at redshift 20, 18 or so from whatever first galaxies were formed. So you have to have a very good count of the dark matter halo. So we are fairly certain how many dark matter halos are there. Then you need to have how many uh, uh, how much baryons went in and how much star formation happened in those halos. So what is the luminosity, UV, particularly the UV luminosity of the galaxies that existed in those dark matter halos. So once you estimate that UV luminosity corresponding to each dark matter halo, then you add them all together, weighting them with their numbers, and then you finally get a total photon budget of the universe, which is the left side here, the rate of production of photons. Actually, rate of availability of photons in the IGN. So rate of production of photons within the galaxy, but then the photons have to go out from the galaxy into the intergalactic medium to ionize it. So what are the factors that are sitting in this calculation? You see here, the dn over dmh is the theoretical dark matter number function. Then the second quantity here is the FB, which is the baryon fraction, how much baryons would have gone in. F star is the star formation efficiency, how much baryons got converted to stars. And then N gamma B is this first factor, and F escape is the how many photons finally were produced, then how many actually escape out of the dark matter halo. So all those factors have to be put in. The modeling is heavily, I would say, dependent. I shouldn't say biased, but I would say dependent on these particular parameters. Okay. For example, the very famous theoretical works in this one, like the 21 cm fast. So it did a very good exercise. Theoretically, it's a daunting task, and they were able to mold it. Model the entire problem and produce some results which are now, are the benchmark results for the SKA and MWA radio astronomy telescopes, okay, for the ionization problem. But the issue lies in these factors. So these factors have been chosen to be constant factors. So like this F escape here, it has been chosen to be 0.1, which basically says you that if there is a fairly big galaxy and it produces, say, 1,000 photons, then 0.1 will tell you 100 will go out of the galaxy, rest 900 will be absorbed within the galaxy. And you use the same ratio for a galaxy which is a fairly small galaxy. So a constant fraction has been used. But we saw the number functions, and that is truth about literally everything in our universe, that the small amplitudes are very high in number. There are far too many small galaxies, okay? So that same fraction is multiplied there, but there are too many, logarithmically too many small galaxies. So you will get the obvious conclusion that the universe is actually reionized by the small galaxy. Okay? If you choose a constant factor there. Of course, there are far too many numbers. I'll come to that. Okay. So I'm just telling you what is the problem. So I'm introducing the problem and then I'll tell you the solution. Okay. So dark matter halos, then star formation or star formation rate or stellar mass, then ionizing photons, and then you multiply with the escape fraction to get the estimate of how many photons are available in the intergalactic medium. Right. So a major goal of JWST was actually to detect all those faint galaxies, because the number functions, if you saw, they kept on rising on the low mass end. So you may say that we are limited by the low mass end. Maybe there are more galaxies and JWST will detect them and we will improve our calculation even more. We will find those hidden galaxies that we are not able to see right now with HST, also with HST, which ionize the universe. So that was one of the white paper motivation for JWST. Okay. But it is correct to extrapolate the smooth trends between halo mass, stellar mass. Is it correct? Like whatever the trends we see, whatever these fuzz factors, the constant values that have been used in this calculation, so how correct those are? Okay. So we'll see that. We can eliminate the problem partially. That was some work that I was doing about 5-6 years back. So you see, in this problem, so if you see this full connection here, dark matter halo to star formation to ionizing photons to escape fraction, this is pure theory. Star formation rate you get from theory by adding one factor, which is F star. But you can say that no. The reionization problem don't need dark matter. From the theoretical point of view, I would say it needs it. But you would say, I will give you the number of galaxies of a particular luminosity or the luminosity functions. So you start the solution from there rather than starting it from the dark matter. Because you already see how many galaxies are there. So you count how many photons will be there. You only have to say, because I'm seeing the galaxy in a particular band, you have to convert it to the UV band. So escape fraction has to be used. So That work was done 5-6 years back, where you actually eliminate the problem. You start right from the luminosity functions to get the estimate of the photon budget. You only have to consider the escape fraction. That how many galaxies of that luminosity, how many galaxies of that brighter luminosity and fainter luminosity. So that we tried. That was the first thing we tried. Here also the same problem is there. If I use a constant value of F escape, obviously your calculation or your result will be skewed towards an answer that says that the faint galaxies ionize the universe, because there are far too many in number. Luminosity functions rise towards the low mass with the low luminosity. So escape fraction is a very crucial parameter. What do we know about it? Okay. So let's see what is the escape fraction from our galaxy. Some observations have been there to detect it. We don't detect anything. You remember for reionization, we need a factor 0.1. In percentage, that will be 10%. We place an upper limit that our galaxy, the UV photons, we are sending out only less than 1%, not more than that. Negligible, not enough. All the observations, even up to redshift 2 or 3 in Lyman break galaxies, they have also failed, mostly up to, I would say, year 2015. They failed to detect any significant escaping Lyman continuum photons. Okay, the photons having wavelengths below 912 angstrom, they didn't detect. Of all the photons that you produce from the star formation process, nobody really finds that any significant fraction of the UV photons they leave out of the galaxy. UV photons, the Lyman continuum photons. Okay, so there's one more thing. But to explain the photoionization background, which is another property measured up to very high redshifts, the paper from Madhav, that you need to have that mean escape fraction of all the galaxies in the universe that should evolve from low to high redshift to quite high values. Okay, so that is another thing we know about the escape fraction. Observational point of view, we don't detect it. This was a paper in 2016. I told you up to 2015, there is no detection. They actually, from the SED curve, they claimed that they are detecting from a nearby extreme starburst galaxy that fairly a significant fraction of photons are escaping. So they placed a number which is roughly, in this calculation, I believe it was, I think 8% after dust correction, and it was about 20% without dust correction. So, which is way up from 1%. So 8% is actually very much close to the value required for reionization models, which is 10% or 0. Yeah, I would say it's more like fairly, because the lack of those galaxies in the nearby universe. And I would tell you that a higher chance of detecting them in the higher redshift universe. And we were not able to go. This is not a Milky Way. This is a galaxy which is called compact object or some starburst galaxy actually. And it's nearby galaxy. I don't know the name of this galaxy, but they had a modeling also. This was a Nature paper, and in that because why the photons are coming out of the galaxy, because most of the photons in a smooth disk, they should be just absorbed. You need to have some channels through which the photons can escape. That brings me into the next point. You need to have channels for a very irregular, inhomogeneous, broken, punctured is a better word, punctured ISM, so that the photons can escape from the galaxy. And then it was detected. Okay. So this was the idea. Okay. This is another rather indirect observation of these two. So I think if people are expert in this one, is the higher ionization divided by the lower one. And indirectly, they claim that maybe the ionizing photons are leaking through in the conical region. Wherever there are outflows happening, they are clearing paths for the photons also to this flow out, the UV photon. Okay. There was a strong idea. So we took a bold step. We said that, okay, so the reionization modeling requires or uses all the time a constant fraction. We will use these new ideas that maybe whenever there is a strong burst, the ISM is opened up or the belly of the galaxy is opened up and the photons will go out. Let's have an estimate of how or what's the fraction of galaxies at a given redshift in which this might be happening. Okay, so a very good quantitative estimate that what is the probability of having a punctured galaxy or punctured ISM is the star formation rate surface density, which is the star formation rate divided by the surface area of the galaxy. Okay, so we plotted a statistical plot and we compared it with the leading cosmological simulation Eagle also. And the blue are SDSS observations, and then the line that you get is from the Eagle simulation. So your luminosity, as it increases from left to right, or the star formation, which is on the upper axis, increases from left to right, the galaxies tend to have a higher star formation rate, surface density. And the significant thing is that with redshift, all the plots are shifting up. So there is a higher probability that you start getting these starburst type of galaxies in which this quantity can be very, very high, and more so, or more prevalence at higher and higher redshift. Now, even at low redshift, because this observation was, this one was a low redshift observation, redshift 0. So you see the histogram for the blue one here. Most of the galaxies are these galaxies, which are way below. Let's say if you place a limit, above the horizontal line, you have punctured galaxies, and below that, non-punctured galaxies. So most of the galaxies at redshift 0 are normal galaxies. So you can't detect any escape fractions from them. Look at the histogram. There is a box there also. So that's the cross I have plotted. So what is the value of this quantity and the luminosity for this galaxy that has been observed at low redshift? So it is that cross galaxy. And from the simulation also, we are able to predict there's a very tiny fraction of those galaxies. Maybe there, not most of them. They don't have that capability from which the photons can escape. But at high redshift, it's very common. It should be very common. So just by looking at that plot, and then that requirement for reionization, that it should, the mean escape fraction should be very, very low at low redshift, and it should increase. Also to explain the photoionization background at high redshift, we could sense that we can build a model from here. So if we create a criteria to estimate an evolution of the escape fraction, then we will be able to explain which galaxies actually ionize the universe. So we took another bold step, and we rather wrote a very provocating title for the paper. So everybody and the entire community was that faint galaxies ionize the universe. So we said the brighter galaxies ionize the universe. So, and the conclusion was that actually HST is already capable of detecting 50% of those brighter galaxies, and JWST will do even a better job in detecting those brighter galaxies that ionize the universe. Remember, we never said anything about the mass. Here we were doing a half calculation. We were deliberately allowing ourselves to forget about dark matter for the time being and only focus on the luminosities of the galaxies and make a statement that the brighter galaxies did. So you don't chase those faint galaxies, but JWST is going to detect a population of brighter galaxies with a very high value of surface star formation rate. Okay, so we made that claim, and there was observational support. So this was a French group which actually plotted this quantity for some other galaxies they detected. One galaxy I showed you, but they had 4 more where this quantity was very, very high, and they detected an escape fraction of 6 to 13%. This was another Nature paper. Okay, so let's fast forward to 2022. We already predicted that the JWST is going to detect the brighter galaxies with specific or the star formation rate, surface density greater than that, and those are the reionizing galaxies. Okay, so these are some of the new observations that came from the JWST field. Before? Very good point. Okay, so that's so it does not mean that if the galaxy is brighter, then it will not be faint at some other point, or it does not mean that that galaxy is brighter, that there is not a identical twin of that galaxy which is actually very passive and having no star formation. So the scatter carries a lot of information, which is the topic of the final result that I will show you. Okay, so let's skip this one so we don't have to look. So this is the paper they published from the first JWST observation from the JADES field. Okay, and then in that paper, citing us, they gave this table. Okay, which is basically the SFR values m star, and they claimed the surface density of galaxies are typically in this range 15 to 180, the galaxies, and they claim that the JWST is detecting these galaxies now which are reionizing the universe. Okay, if I place these galaxies, they will be somewhere here, the new JWST galaxies in this upper bunch that we were saying always that reionize the universe. Okay, so and then they didn't stop there. because 2022 is now old, 3 years now, more galaxies. Again, claiming the same thing, that you can plot the sigma SFR and the escape fraction. When the sigma SFR is higher, the escape fraction of these galaxies are high. Okay, so these are all the observational confirmations for that theoretical result. So let's take a pause here. So remember, we started from the stars, luminosities of galaxies, which is 1/2 of the problem. From the theoretical standpoint, we should, as a theorist, I should start from the dark matter halo and then explain the entire problem, which is, theoretically, we have to be detached. If you just focus purely on observational modeling, then you will be blocking one side of your predicting power. So no, we start from dark matter halo and then let's see what happens. We go back. So the 21 cm fast is the leading code, which uses these constant fractions. And then now we wanted, okay, all these brighter galaxies that are detected by JWST. So we already predicted and they have been detected, but we want to make a prediction about in which dark matter halos those galaxies are living. What are the masses of dark matter halo? Which I don't know how you will measure it. I think it was a very good question. So JWST is still able to detect faint or bright because these are luminous things, baryons. But what are the dark matter halo masses of those galaxies? I don't know how or what instrument is actually going to detect them. So we wanted to make a prediction on that. So we went back to the blackboard or whiteboard. And then other thing that we were knowing is the galaxies have two different categories, you can say. I mean, they are more quiescent or gentle galaxies having a continuous star formation, or they can be very violent, high sigma SFR or high specific SSFR galaxies, which are opening their bellies and opening or puncturing, having puncture disks for the photons to escape. Okay. For example, this is the famous main sequence of the galaxies, which has become popular. The starburst galaxies are usually above the main sequence. They are in the scatter. Most of the galaxy will lie on the main sequence, where their stellar masses are on the x-axis and the luminosities are on the y-axis. Luminosities are correlated with the stellar masses, and that's how you get this main sequence. But the galaxies that ionize the universe, they will be off the main sequence. Okay. We did a very interesting plot. This was for some other context, though, to explain the peculiar carbon abundances and other metal abundances in the stars that you find in the Milky Way. We said that those stars formed in early progenitors that were starbursts. For that, we needed how does the star formation happens in a galaxy? So things that we see them today, of course, they didn't start like that. Okay. So our economy is stable, but it probably didn't start like that. There were hiccups in the beginning. Any engine of a car, when it runs on the road at 100 km per second or so, it runs smoothly. But when you start it, there are always hiccups in that, a breathing episode period. So when the first time the galaxy forms star, it should form like this. 0, when gas comes in, forms a first burst, fluctuations, and then it settles into a gentle star formation. So that is the central idea. So you would expect in the smallest dark matter halos, when the baryons go first, then initially the galaxies will be forming stars and stopping, forming, and then as the galaxy grows, it will become settled. Okay, more and more this type of hiccups or bursts are expected in the high redshift universe, because that's where most of the galaxies are starting their journey. Okay, there are two phases to star formation: an episodic bursty phase, and then a regular, like a Milky Way type of gentle phase, which is approaching a passive, non-active phase now. Population. So I have, true, I don't have time to talk about it, but I have two papers on which I was looking at metal poor stars in the Milky Way to get that. Yeah. So then we came to this period. This is the starting point of this particular paper that appeared this year. So you have the Eagle cosmological simulations in the background as a consistency check, and the galaxies that are detected by the JWST different surveys are as shown as the points. Okay, so you see this main sequence type of thing both in the simulation and in most of the JWST detect data. But then there are these claimed to be reionizer galaxies, which are blue points here and the same blue points there. So the quantity plotted is the specific star formation rate, which is star formation rate divided by the stellar mass, and here it is the star formation rate. Those are above. Okay, those are the galaxies that reionize the universe. Both the quantities in this plot are quantities that can be observed, the stellar mass and the SFR. So the simulation is also doing a good job of getting the scatter right, and the scatter is more so higher towards the lower mass end. But know that these galaxies are not faint. See, if you follow this track here, these galaxies are faint, but those galaxies are having high star formation rate, they are not faint, they are brighter galaxies. We wanted to go to dark matter halo because we have a consistency check that allows us to actually leap and take a step further and use the simulation to plot the x-axis as a dark matter halo mass. The same plot, now the observations don't allow us, but the m star can be converted to mh because the simulation in the simulation we have it. This is the x-axis. So we have a m halo and the specific star formation rate, and that's where most of the galaxies at high redshift, if I see this one, they are jumping up and having a huge scatter around 10 to the power 9 or so. Okay, and we tested for resolution also. It's not because of the resolution, purely a feature. At redshift, at a halo of slightly above 10 to the power 9 halo mass, it begins the entire process. Because you know, this is where the star formation is roughly beginning in the universe. We use that information saying that how many galaxies are having that above average thing. We associate some fiducial number of escape fraction to that, say 20% or 30%, and then rest of the galaxies in that bin of halo mass don't have anything, to get an average F escape, which is on the y-axis here, and then the average F escape for the population is high here, and then it is low, settles to a gentle slope. It really doesn't matter where you cut it off, and we check that hardly there will be any implications for the final result that we have. Okay, so and we fitted this particular thing from the simulation with a skewed Gaussian function, which is shown as a solid black line in this plot. So this is a big improvement. So you remember the calculation 21 cm fast I showed to you that uses a constant number, but we have a very good number now that we developed from the synergy of Eagle simulation with the JWST observation. We implemented that in the 21 cm fast calculation, changed the entire machinery, how the escape fraction works, and implemented this one. And then this is the evolution of neutral fraction in the universe compared with the various observations that exist for this particular plot. So we had 3 models, and the black is our leading model, and then dashed black is where we cut off at the high mass end. Okay, so compared to all the other models, if you see, we claim that black does a good job, but anybody can say that the error bars are too high. But nonetheless, it is a well accepted fact now that the reionization got to be more and more instantaneous. What do I mean by that? That it has to happen very fairly rapidly. So any models that can produce a rapid reionization are the favored models, rather than the models that do it gently, which are the older or other variations of our models, basically the purple and blue line. The black one does it fairly rapidly. Why does it do rapidly? So that's one thing. And the other thing is that we also plotted all the quantities that are relevant for the 21 cm centimeter observations, like the brightness temperature is shown for all 4 models here. And to look for is the SGE model. This G10 is the model in which we specifically say that I shut down the star escape fraction from all the other halo masses and keep it only in the 10 to the power 10. And then I keep it only in the 10 to the power 9, or I keep it only in the 10 to the power 8 halos, just to see what are the effects that are finally giving rise to the properties that we are observing in the SGE model. Okay, and this is the XH1 map. Okay, so now what you see is that there is a twofold thing happening here. There are small purple dots also, and then there are big yellow regions also. The big galaxies create big regions. The small galaxies create small regions. So both the things are well represented here. So the 10 to the power 9 halo, where the peak is there, that gives rise to all these small dots of porous structure, and the bigger islands are given by the 10 to the power 10 halos, which have a tail, a finite but non-zero tail on the high mass end, where there are still some bursts. So the reionization happens very rapidly in the black model, which is the skewed Gaussian model or SGE model, and we say that the rate of change of this quantity, the mean ionized fraction, you see it is fairly low at the beginning, and then it jumps up very quickly, and then that's where it ionizes the universe. So it's a very optimized model in that sense, the escape fraction model that we got from the comparison of JWST data with the Eagle simulation. So it is optimized in the sense that it starts off late, but it starts because of the 10 to the power 9 halos, and then successively the 2 times more mass than that and 3 times more mass than that, because the function is not a delta function. It has a tail like this. Those halos, they come in and contribute to raise or have a catalytic effect to get this quantity way above the rate of ionizing the universe. This is basically the rate of ionizing. This is the final prediction from this paper, which is the 21 cm fast power spectrum. And we get this particular power spectrum, and we compared it with the earlier benchmark power spectrums from this 21 cm fast code. And in the comparison, we see that we have a slightly late peak in the 21 cm spectra, shown by the blue and the black model of ours, compared to the earlier one, which is purplish or reddish models, and the peak's prominence is also higher. Now, these theoretical predictions are still, you would say, far away from the flagship observers or observational surveys like the MWA or so, which are the sensitivity limits shown as points in this particular plot. It's a slight up from there, but that's what pretty much say that if they finally manage to detect it, and if indeed this is true, they are going to detect that power. That is the claim that we are making. So I think I have said fairly enough, and I will stop and won't read through the conclusions. So I will take the questions from here. Thank you very much.
Mahavir, for the interesting talk and the questions.
Consider the dark matter halos, or if you consider dark matter halos, then what would we maybe be confused about? So, what would be the difference in the JWST result? I mean, so if you are using JWST result to calculate the escape fraction,
ideally there should be no difference, right? That's what is the second paper we are working on. But it gives you an opportunity to get the F star right.
Okay.
Still, from the dark matter to F star, we have a trust on the 21 cm fast modeling, and we trust on the universe, and we only tweak the escape fraction. But truthfully speaking, the two parameters, the way they are appearing, F star product with F escape, why there should be two parameters? You go from dark matter halo to UV photon luminosity. So that's the next paper we are doing. There should be no difference, and to get that no difference, how your parameterization should be changed, or what should be the theoretical. That's what we are doing. There should be no difference. After all, it's the same galaxies that ionize the universe. We just wanted to answer the backward question, which is like which dark matter halos these galaxies will correspond to. That's the question. So I don't know about the terminology that way, but I have all the galaxies from JWST on my plot there, the blue points and so.
So these are basically quasars.
But it is very much evolving.
Yeah.
I would have to look whether indeed the red dots are those that I have.
Okay.
Or maybe they are claiming to be something else. But you see, there are many main sequence stuff also they are getting. Those are not relevant for the reionization. It's only the brighter ones.
Yeah.
Red dot, by the name, it seems to be faint.
Yeah, it would be difficult for them to estimate this sigma star, probably surface brightness.
No, they do. It can be. You can get the size.
Yeah, it's very small. It's very tiny dots.
Tiny, and you can always say that there are uncertainties on that, but you can have a comparison of the 10 galaxies that you observe, what is the low sigma SFR and what is the high sigma SFR, and that is pretty much is required.
Actually, I have a question that means initially you were telling that fainter galaxies are more contributing to reionization. And you were saying that because they are large in numbers. But did you means try to normalize with the numbers of fainter and brighter galaxies and then try to means
normalize in what sense?
Means with the number of galaxies, fainter or bright?
I think luminosity functions are already normalized. So, see, fainter means if you build a luminosity function, so you have already the count of faint galaxies and the bright galaxies. So you have that count that's already coming from the observers normalized, and then you say how many photons are coming from there, not the normal photon. Photons below 912 angstrom.
No, yeah, means you are saying that fainter galaxies are more contributing, means there is a bias because they are means more in numbers.
More, yes, because of the numbers. Yeah, true.
Yeah. So means if we just normalize it, means do our results get changed or they remain same?
So see, more in number compared to the bright ones, and the entire function is normalized. So there is a one big function you have, it's called the luminosity function. The faint ones are significantly, logarithmically higher in number compared to the bright galaxies. You only have to just say that those are also contributing 10% of their photons, and these are also contributing 10% of their photons. But they are far too many in number. If they are both contributing with the equal escape fraction, then the biggest contribution will come from the faint galaxies because there are too many. So that's the thing.
I just looked into that. You're considering the UV emission only. So if you go to the higher energy, then what will happen? I mean, so let's say the
Right.
X-ray, there are few are the observed in X-rays and all.
X-ray would come mostly from the hot
region, yeah.
hot region and hot cesium. So I wouldn't say it is relevant for the reionization as such, but I would say it is relevant for the heating phase.
Yeah.
So you see, the problem is very rich in a way. Reionization happens between 9 and 6, but the heating happens from 12 to 9.
12 to 9.
So that's worth looking at. All the JWST galaxies, or what is the X-ray emission from them, and whatever heating models have been used based on the HST and previous ones, how do the two compare? How would the heating epoch will change because of that? And it impinges on the F star parameter. Now, here the UV photon escape and UV photon thing that I was talking about depends on the F escape parameter. The heating also depends on a star parameter. How many stars you formed and then X-rays were produced. And I would say hard X-rays or the soft X-ray?
It's a soft X-ray.
Soft X-rays. So
it's close to the UV, for example, if you do the soft X-ray and there are soft X-ray emitter as well.
True. So it's the diffuse emission.
Diffuse emission, something.
Yes, it's from the ionized gas in the galaxy.
Yeah.
So yeah, I mean, you would say that supposedly it has to be neutral first, then the stars form, they ionize it, and then the diffuse emission comes. But I think for the heating of the universe, if I'm not wrong, has to be from hard X-rays. You have to have a model for the hard X-rays that go and heat up the intergalactic medium. Because otherwise, if it is from the star formation, it will still proceed. I think you are right. So see, I'm mixing up so many things here. So the soft X-rays that will be coming because of the star formation, they will leak out and start up heating. That's why F star is important in this process between 12 and 9. Yeah, so it has to be modeled.
Okay.
Did you, okay. So did you consider the initial mass function for the star formation be different from the current one? So people consider that initially the size.
So right now, whatever was there is Krupa-Chabrier, which is the standard mass function. Yes, you can have a more top-heavy initial mass function and say that the population 3-star, which is another leading line of research that is the JWST detecting the oldest generation POP3 star and connected top-heavy initial mass function, which is skewed towards the POP3 stars. So no, that is not done here. We do not consider, we consider standard star formation with Chabrier mass function.
Okay, so if no more questions, thanks again the speaker.
Thank you. Chabrier Salpeter. Salpeter is the old one, Chabrier is the slightly tweaked version, which is the standard for the normal population. So Salpeter is a standard power law. Chabrier is cut off at the low mass end. But they are very similar. They give results which are very similar because you are mostly concerned with the high mass ones. Low mass ones are not going to impact it. Okay, so you can close.
So about that Eagle thing, how do you get that happening?
Oh, Eagle is almost a replica of the universe. So it's a public database is there. And there are two things. What do you want to do? If you want to re-simulate, it's a time-taking task, but you can do really interesting things just by the data that is available from the original simulation, which is publicly available. There are two things. Which one are you interested in? Rerunning the simulation? Yeah, so you need significant computational power. So that was run on the Dirac facility in UK on 5,000 cores for a month. So difficult, but you can do very simple toy projects with the gadget code, which is the basis for that one. For individual galaxies, that I suppose can be done on small clusters. So yeah, for that you don't have to look for Eagle as such. There is a publicly available code called Gadget. You can simply download that code and start with the exercises in that particular code. Okay, for individual galaxies. It's called Gadget. There is a newer version of that. It's called Gadget 3. Okay, so that's it. Hello? Yeah, I think Nachiket named you only. She was working something.
He came for 3 months and then he told me that he's working, but I didn't know that.
Yeah, he was working with me.
Yeah.
Yeah, I didn't have much time, so with a lot of teaching and other things. So he came to me. I said, whether you, it goes on the